share my screen. Okay, so I have 3 D flip-flops, and I'm going to turn the computer over. And I always have a clock, and so, you know, if you're on the test and you're like, I don't know what to do, and you're starting to panic, you know, you can always draw a clock, you know, that's going to be in there. And we'll have our output Q. And depending on the problem, it may be useful, it might not, to also have the Q bar output, because if one of the things your register does is to take the complement of something, it might be useful just to go ahead and have that handy. Okay, and we have to look and do different things depending on our inputs, which are S0, S1, and S2. So that means we're going to have a multiplexer. And so our multiplexer, I'm going to draw the multiplexer like this. Usually it's a little trapezoid shape, but because it's an 8-to-1, I want to have more space here. And I have 3 inputs, S1, S2, S0, S1, and S2. So I will have those here, S0, S1, S2, S0, S1, S2, S0, S1, S2. And those are what control what output I get from my multiplexer. And so the output from multiplexer 1 will go into D1. The output from multiplexer 2 will go into, it's supposed to be a D right there, will go into D2. So this is flip-flop 1. Oh, actually, I have XYZ. Outputs XYZ. So I will call this output X, this output Y, and this output Z. And so I'll label those on my circuit. So here's X, here's Y, and here's Z. So where that Q bar output would be handy would be if one of my inputs had to do with X bar, Y bar, or Z bar. Okay, and then now I will label the inputs of my multiplexer from 0 to 7. Alright, so now comes the fun part. Alright, so if we have 0, 0, 0, then the register outputs are unchanged. So that means that whatever Q is, that should be what Q next is. So that means coming into the 0 input on each of these should be the previous Q value. So, I will take from this one, it's going to go into the 0 input. and from this one into the 0 input, and from this one into the 0 input, because when it was 0, 0, 0, it's supposed to be unchanged. Alright, so then the next one says, if you can't see it, rather than scrolling back and forth, I'll just read it to you. The next one says, for 0, 0, 1, it's supposed to shift right by 1 bit, and a bit enters on line LN. Okay, so I have the bits are supposed to shift right. So that means that if I had originally had, so if XYZ was originally 0, 1, 1, then shifting right means that my next X, Y, and Z will be the 0 is going to go to the Y, the 1 goes to the Z, and then whatever line in is, that's going to go to the X. And that is when I have S0, S1, S2 equals 0, 0, 1, which is binary for 1. And so I need to have, I'll have some variable called line in, and so I'll add that. So line in. And line in is going to be what becomes X. And then what was X becomes Y. So I had my X value right here. So I'm just going to take that over here and put it in 1. And what was Y becomes Z. And I'll take that and put that into the 1 input for Z. Okay, so then if it's 0, 1, 0, we shift left by 1 bit, and the bit enters on R in. So this is the opposite. So this time, Z goes to Y, Y goes to X, and something new comes in. Oh, it wasn't line in, it's just left in, I guess? Left in, right in. Okay, so we have another variable, R in, and that is going to go into Z. And what was Z, which is this line right here, that's going to go to Y. And Y is going to go to X. And then 0, 1, 1 says load A to X, B to Y, and C to Z. So I have new variables, so this which are A, B, and C. So when it's 3, that's what we get. And then for 4, complement outputs X, Y, and Z. Okay, so I could use the Q out on these, but since I have the signal right here already handy, I'm just going to use a NOT gate right here. So this is going to be the NOT of X, and the NOT of Y, and the NOT of Z, and that goes into input 4. Input 5 says rotate right by 1 bit. So rotate right, so let me show you what rotate right means. So if I had 1, 0, 1, rotate right means that, so this is X, Y, and Z. The X goes to the Y, so Y becomes 1. The Y goes to the Z, so Z becomes 0. And then the Z goes around, it rotates around and becomes X. So we need X to go to Y. So X, which is already going into line 1 right here, I can make it also go into So I can make it go into input 5, and y, which was already going into input 1, I can make it go into 5. And I believe I had z, my output from z, going somewhere. I don't know where, but I will just grab it right here and make it go to 5. And then 6 is rotate left by 1 bit. And so z goes to y, y goes to x, x goes to z. So this is z right here. It's going to 6. This one is y. If you look, it's connected right here, which is y. So it'll go to 6. And x goes to z. And this is x right here. And it'll go into 6 for that. And 111 is clear the outputs, make x, y, z, 0, 0, 0. So that just means I will have 0 going into each of these. Okay, so before I go on, even though the problem doesn't say to do this, I think it would be useful to do the Verilog because that is what people said they had the most difficulty with. But before I go on to that, are there questions about what I did so far?
Can you show the difference between rotating it and shifting it, like
Yes.
to the right, or like rotating it to the right again?
Yes, I will. Okay, so first I will shift right. So shift right means that everything just moves one position to the right. So it becomes 1 0 1 1 0 1, and this bit gets lost, so this 0 just goes nowhere, and I have a new input coming in to be whatever this is. So I don't know what that is, x, whatever that is. Rotate right means I do the same thing, except instead of this 0 just disappearing, it comes around and it becomes the bit on the other side. Does that make sense?
Yes, thank you.
You're welcome. Okay. Any other questions before we do the Verilog for this? Okay. All right. So we're going to do, this is going to be like the general output of what we're going to do is going to be the Verilog for how you would do any kind of register. So this will be really handy for you to have. So I will call this module register. And let's see what we have. We have our input was S. We have outputs X, Y, Z. And I'm going to make S a 3-bit variable. I had LN. I had RN. I'll have a clock. I'll have I will have I had A, B, C, and did I have anything else? Okay. All right. So, all right. Now I'm going to make this very. If we come up with something else, we'll add it in. I'm going to make this very general so that you could use this for another another problem if you needed to. So I'm going to say parameter n equals 3, and I'm just going to use this to stand for how many flip-flops I have. And I'll have input 1:0. No, I had 2:0 for S. Actually, probably might be easiest for me to say n-1:0 for S, because then I could reuse this for something else. Now, just a note here. So if you had an output or input that was more than 1 bit, you could have those as vectors as well. So like, for example, instead of X, Y, and Z, I could have my output, it would be output reg n-1:0 Q, and input n-1:0 L, like if I had to load a variable. So like if rather than outputting, because I'm inputting and outputting just separate bits here, but if I needed to do it as just one variable, I would have it like use it as a vectored signal. Okay, so, and I could have like I'm doing with S here. Okay, but I don't, so I have input A, comma, B, comma, C, comma, clock, comma, LN, comma, RN. And I have output reg. Now the reason they're reg is because I'm going to define them in the always block. And whenever you have flip-flops, that's going to be what you're doing. You have calculations that you're doing inside an always block, and those are going to be reg. And so output reg X, Y, Z. I'm also going to have, I'm going to have 2 always blocks. In one of the always blocks, I'm going to have what my next output is going to be. So I will have just reg, and I'll just call it next X, next Y, next Z. Okay, so now I'll have my always block. Always at, and this is if anything changes except for the clock. because this is what I'm doing right now is the what part, not the when part. So I'll have one always block for the what part and one always block for the when part. And so this is when any of my inputs change. So that would be any of these, not XYZ because those are outputs, and not the clock because that's going to be something different. But whenever any of these change, then I will want to make a change. So now I'm going to have a case statement. I don't think I need a begin here because I think all I'm going to have is one case statement, but just in case I'll put one in. And then I'll have case and S. I want to make sure I get my syntax right. I am terrible about remembering the syntax for different languages. Let me just look it up real quick. Okay. Okay, so case S, and then I could have this either as in parentheses, Yes, in parentheses. Okay, and then I could have this either as binary or as just its decimal equivalent. So I could do either like we have here, 2 apostrophe B00. So 2 apostrophe B00, well, it's 000 because we have 3. Or I can just do the number 0, which is probably what I'm going to do because that's easier for me. Okay, now I have to have a begin here because we're changing more than one thing with each. So when you have more than one statement, you have to have a begin and end. So with 0, they were not changing. So next x equals x. I'll use a blocking assignment, a non-blocking assignment. Next x will be x. I thought I said to ignore that. Next y will be y, and next z will be z. And then I can end that case. And then I have case 1, and with case 1, who remembers what case 1 was? Shift right by 1 bit. Okay, so then next x becomes rn. Oh, it won't do ignore every time? Okay, that's okay. Next y is x, and next z is y, and I needed a begin there. Okay, and then case 2. And 2 was shift left by 1 bit. So X will become Y, Y will become Z, and Z will become LN. And then we have case 3 was, I did start with 0, right? Yeah. So case 3, load A to X, B to Y, C to Z. So and do it over here on this side. So 3, and see if I can drag this over now. Yeah. Okay, 3. I forgot my begin and end on 2. So for case 3, becomes A, B, and C. And then case 4 was complement. So X, next X would become not X. Next Y would become not Y. And next Z would become not Z. That's case 4. And case 5, I believe, was rotate. Rotate right. So rotate right means right X is going to become Z. Y becomes X. And Z becomes Y. And then case 6 was rotate left. So, yeah, okay, so X becomes Y, Y becomes Z, and Z becomes X. And then case 7 was to clear all inputs, or make them all 0, I think it was. And then at the end of all that, I would have end case. Yep. Okay, now notice that I did put a begin on my always block. All I really had in my always block was one case statement, and so since it's it looks like a lot of statements, but it's all just one case statement, and so I could do without the begin and end on the always block, but because I put it there, I do need to end the always block as well. So end. And then I need to have my next always block, and so that determined what the next output was. Now the next always block is going to be when it happens. So the next always block will be always at clock, always at positive edge clock, or negative edge, depending on if it's given. And then always at positive edge clock, and begin, and actually I know I do need a begin here. I'm going to have X will become next X, Y will become next Y, and Z will become next Z. And then I can end that always block. And then I can end my module. I say I can. Recall, there's no semicolon on that? No, it seems like there should be. And there's no semicolon on end case either, but that's not that important. I doubt you get taken off for a wrong semicolon. Okay, so that is both that problem and its Verilog. So, and kind of a general template for how the Verilog would go. Now, I could have, let me just show you another example here. Let's say that I had, I'm going to do this slightly differently. Let's say that I'll do a new page. Hold on a second, it may look like I'm going away, but I'm just trying to fix my computer. I'll just write. Okay, it's not accepting keyboard input. So let's say that I have instead my output is Q0, Q1, Q2. So my output is a 3-bit number. That's my output. And my input is, I also have an input. So let's say that I have a 3-bit register. And this time I'm doing it as a vectored signal, a 3-bit register. And if S is 0, 0, it's, let's do rotate right. And if S is 0, 1, let's do rotate left. And if S is 1, 0, let's load L, when L would be a 3-bit number. And If S is 1, 1, then let's load 0. Okay, so in this case, my output is 3 bits of vectored signal. So I would have in my code, so I'd have output reg, and in this case, I'll just go ahead and use 2:0 instead of n-1 q. I'll have input 2:0 L, input 1:0 S, and let's see, do I need anything else? Yes, I need reg, and I will just call it next, or maybe next state. Well, I need to give it size because I'm going to have it. So I will do 2:0 next state. Okay, so then in my always block, I would have always at S, comma L, that's it, S, comma L, and then I could have a case statement again, case S, 0, colon, and then in this case, what I could do is I would say next state becomes, now when it's 0, I want it to rotate right, and so I would want Q1, comma Q2, comma Q0, because my output, so I'd have my 3 flip-flops here, and so I'd have Q0, Q1, Q2, and if I rotate right, oh, I rotated left, so rotate right, so I did it, good thing I drew it out. Okay, so this would be Q2, Q1, nope, Q2, Q0, and Q1, because my next state here would look like Q2, Q0, and Q1, because I rotated right, so Q0 goes, this was originally Q0, this was originally Q1, so originally Q2, so Q0 goes there, Q1 goes there, and Q2 goes around there, so I write it in that direction. So rotate left, that's what I wrote last time because I don't know my left from right, would be, that one would be Q1, Q2, Q0, and then 2, I can just have next state becomes L. L is already a 3-bit number, so I don't have to put it in the curly brackets or do anything with that. And then 3, next state, and I would write it as a binary number, just for ease of use. I believe it would work whether you did it as a binary number or a decimal number, but I would do 3 apostrophe B 0 0 0, and then end case. Notice this time I did not do a begin and end on my always block, because I knew I just had the one case statement. And then I would have always at positive edge clock. What was my variable? Q becomes next state. And then end module. Okay, so questions on that? I wanted to make sure that I got some good Verilog in there because last year that's what they said they needed the most. So I'm going to stop.